Why are there so many songs of rainbows and what's on the other side? Rainbows are visions, but only illusions. Rainbows have nothing to hide. Okay, I'm getting a little better. Better than yesterday, at least. Okay. Anyhow, why am I singing about rainbows? Well, today we want to get things started, and I want to start it off right. We're going to be talking about the atmosphere. So over the next week or so, we're going to be kind of traveling through weather, climate, what the atmosphere is, so forth and so on. So there we go. I have a picture of a pretty rainbow with some nice storm clouds. And if you're reading this or watching this podcast the day that I recorded it, there's been some interesting weather. In fact, had some high winds, had some heavy rains, some hail, heard a little thunder, and some blue skies. So without further ado, we're going to be learning about why these things happen and why they are important to us. So in this presentation, you'll be exploring what the Earth's atmosphere. You'll be able to, number one, distinguish between weather and climate. And that is an important distinction between the two. One that even people in our government tend to get wrong. Or misunderstand, I should say. We're going to break down the composition of the atmosphere. In other words, talk about what gases are we breathing, and examine the properties of the different layers. All the layers of the atmosphere, as you get further away from the Earth, they start to change. They start to behave differently. So that's what we're going to be doing today. So we take a look at the Earth. Here's the Earth. It's a big, beautiful planet, isn't it? It's really like no other planet out there. We're really unique in that, okay, other planets have atmospheres. But our planet is a planet that has an atmosphere that is just perfect for the size of, just perfect size for the living creatures on it. What makes it unique? It's the right temperature, it's the right composition for everything that we need. The unfortunate thing with that unique is that we go somewhere else, we don't have the same thing. So what does it have that's unique? Well, first of all, one of the things that's unique about the Earth is the fact that it has liquid water on it. And because it has liquid water on it, that liquid water has the ability to evaporate and become part of our atmosphere. And where does that liquid water actually come from? Well, that liquid water actually comes from, believe it or not, volcanoes. The Earth didn't start off with oceans and rivers and lakes and streams. It came from volcanoes doing something called outgassing. It was all that stuff was inside of the rock at first. But as volcanoes erupted, it put things like water and carbon dioxide into our atmosphere. And it kind of shaped early on in the Earth what the atmosphere was really actually like. But what's really unique about the Earth's atmosphere, and it separates us from planets, say, like Venus or Mars, is that these crazy creatures right here, kind of at the bottom over there, those crazy creatures are called stromatolites, and those are creatures that were really kind of plant-based microscopic organisms that clustered together in these great big old colonies. And what was important about those plant-based microorganisms is they were the first plants to be able to take in sunlight energy and carbon dioxide. And the unfortunate thing about that for these plants, these stromatolites, is that once they started taking in that sunlight and carbon dioxide, well, you have to have a byproduct. You take in something, you have to give out something. And what they gave off was energy. And not energy, oxygen. And that's because of those microscopic organisms, that's where we get the oxygen that we breathe today. So if you think about it, while those stromatolites were early, probably about a billion years ago, I've seen anywhere between 520,000 to a million, 520 million to a billion years ago, that these things first started appearing on the Earth, and doing that process of photosynthesis really started to change the composition of our atmosphere. And it changed it so much that it actually caused a mass extinction with these stromatolites, because they were literally polluting the atmosphere with oxygen. There was too much oxygen, the stromatolites would die off. When the oxygen started disappearing from the atmosphere again, then what would happen is they would bloom and grow, and we would have a mass amount of stromatolites again, producing more oxygen. Pretty soon we eventually reached a balance to where we have the oxygen that we need for survival for, well, humans and other animals. We're at that point now where we could live. Venus doesn't have that. Mars doesn't have that. They're still kind of outgassed by things like sulfuric acid and carbon dioxide and other gases that makes it unbreathable for us. So as far as we know, there's no other planet that has life on it that has produced oxygens that would make it to where we could actually go to live on it. Not in our solar system, and as far as we know, not as far as any other solar system. So, we even look at the United States. This is a weather map of the United States. I don't think this was this week. I think this was just a random image that I had. But I kind of looked at this image and I'm like going, this is kind of like a typical image of the United States. And we're so diverse because we're kind of right in the middle of so many different weather patterns. You could be in Green Bay, and it could be freezing cold in Green Bay. I know it doesn't say that in the picture right there, but during the winter times, it gets so cold that even the ground freezes over. And it's called frozen tundra. If you go down to Florida, it gets hot and muggy. Anybody ever been down to Disney World down in Orlando, Florida? You'll see, you've experienced as the day progresses, it just gets hotter and hotter and hotter and muggier. And when I say muggy is just a fancy, as kind of a common term for humid. We get into Phoenix. It's still really hot. In fact, it's hotter in Phoenix than it is generally in Florida. But it's what they have a dry heat, and it feels really different. A lot of people have a lot more problems when it's 90 degrees in Florida and humid. It's actually more difficult for your body than it is in Phoenix. And part of that is because when it's humid, your sweat can't evaporate to cool you off. But in Phoenix, the sweat evaporates so fast that it keeps you cool. So 100 degrees in Phoenix feels cooler than 90 degrees in Miami. The other side of that is it's kind of dangerous because the sweat evaporates off you so much, your body constantly produces sweat. And walking around Phoenix, you have to carry water around because you will dehydrate, and you don't think that you're sweating, but you are. You'll dehydrate really, really, really fast. That's a problem in that area. And then there's Seattle. You know, the weather's perfect here in Seattle, right? Well, somewhat perfect. There's no extremes here. It's not very often that we get very big storms. It's super rare to ever get tornadoes. It's temperature never gets oppressively cold, never gets super hot, and there's a reason for that. And those are the reasons why these temperatures are so diverse in the United States. Why they I forgot what I was going to say. Why the temperatures are so diverse, why we have different climates all over the place, why we have weather. That's all things I want to actually get into with today's lesson. All right, so weather. It's important. It's the air that we breathe. It dictates how we dress. It determines what crops we grow. I mean, you just can't grow apples like we grow apples here in Washington and Arizona. We can't grow oranges in Washington like they grow down in Florida. And that's all because of the state of the atmosphere in these areas. Does that atmosphere have moisture? Does it have heat? Does you get enough sunlight? All of these things, looking at that weather on a long-term basis, that will determine what kind of food you can grow, what kind of foods grow best. You just can't grow wheat in the middle of the desert. So you just can't send a bunch of wheat to the Sahara Desert and say, hey, you guys just grow some wheat. It doesn't work that way, because wheat requires a certain amount of sunlight, moisture, so forth and so on. So everything that we do is affected by weather. And this is why I think it's kind of a shame that we were going to miss out on doing this unit this year, is because weather is like one of those most important things. It affects your daily life. Right down to, is there going to be a traffic jam on I-5 that could have something to do with what the weather is that day? So where do we start? Well, let's start the way that most people get just wrong. And that is weather versus climate. A lot of people think weather and climate are the same thing, and unfortunately there's a big problem with that. Weather and climate do talk about the state of the atmosphere, but they're comparing the atmosphere in two different ways. So what's the difference? And that's what I want to get to first. Weather is the state of the atmosphere at a given time and place. And so what I have here is, you can see that this is the forecast. This is the weather observations and forecast for Seattle. I did this last night, which would have been March 24th. At the time it was raining, so the type of precipitation we had was rain. It was 42 degrees outside. The wind was blowing at 3 miles per hour, so a gentle wind. An 84% humidity. We'll talk more about what this 84% humidity is, and that's relative humidity. They tend to forget to say that, and that's an important concept. Dew point 37 degrees. That's 37 degrees is what point will the air no longer be able to hold the moisture. So you'll start getting things like fog on your windshields or dew on the grass. The barometric pressure, how much air is pushing down on you. All of those things are a measurement of what was going on just yesterday. And that is the weather. And what scientists do, and the type of scientist that studies weather, is called a meteorologist. Meteorology is the study of the state of the atmosphere. So what is our atmosphere doing? A meteorologist is a person that interprets those conditions and tries to make predictions based on previous observation as to what's going to happen in the future. So if you look down below where it says the next 36 hours, what you see is a meteorologist is making a prediction based on observations, not just about where we are here, but in the areas that surround us. Is there cold air coming in? Is there warmer air coming in? Do we have more moisture coming in? What happens? Which way is that moisture moving? So they have to ask themselves a lot of questions. And there's a lot of questions in meteorology. I know a lot of people tend to hate the weatherman because the weatherman sometimes says it's going to be sunny tomorrow and then it rains. Well, the reality is, if you actually watch the news and you record what the weatherman says every day, chances are he's going to get it right. And that's fantastic that we have such knowledge and such good technology to be able to predict the weather, because there was a time where you could not predict what the weather was going to be like. It could be nice and sunny outside in the middle of Kansas. You go out for a horse ride, you're 20 miles away from home, and then suddenly a cold front comes through and brings in sudden and intense rain. Suddenly you find yourself on a horse out in the middle of nowhere, unable to get home, and you get something like maybe like a flash flood. People who lived in the South never had any idea that hurricanes were about to hit, and people died because of this. So our advancements in technology and trying to predict the weather, these meteorologists trying to predict the weather and using all these tools, is an important advancement. However, what it is not is to say the weather in Seattle is generally rainy. That's actually not a weather statement. When you're talking about the weather, you can say, well, today it rained. But when you say generally it doesn't rain, doesn't mean it rains all the time. It does mean that, yes, we do get a lot of rain here in the Pacific Northwest, and that's generally what the weather is at any given time. If we were to predict that sometime in February, is it going to rain or not rain? If you said it's going to rain, you're going to have a pretty good prediction as to being right. So what does it mean when I say that generally it's rainy in Seattle or it's generally dry in the desert? What do all those things mean? Well, that's talking about something that's a little bit different. That's talking about climate. Now, climate is the study of an atmosphere based on long-term observations of that area. And I don't mean like Federal Way. I don't mean like Seattle. I mean over a large area. We're talking like maybe of the entire Pacific Northwest, or something that defines generally the weather patterns that dominate that area. So maybe not the Pacific Northwest, maybe the Puget Sound down to Portland region, where generally speaking it rains more often than not. We have more rain days than we don't. That is the climate for this area. And we have things that kind of reflect that climate. We have a lot of trees. We have what's called a rainforest. Rainforest only exists because the climate here is rainy. Maybe you have an area like Southern California, or Arizona, New Mexico. Those areas typically are dominated by warmer temperatures and lack of rain. Does that mean it doesn't rain in Arizona? Absolutely not. In fact, Arizona does have a rainy season. But if you pick a random day in Arizona and you had to lay money down as is it going to be rainy or sunny, you're probably going to lay your money down on it's sunny. That is an example of climate. So climate kind of says this is what the weather like in general over a long period of time, and not a specific place, an entire area. There will be exceptions to that. And climates do change over time. Would you believe that here's getting the picture up here, this is the Sahara Desert. The Sahara Desert is, well, pretty much all covered in sand. It doesn't get much rain. There's very, very little rain in Africa. That part of Africa, I should say. There's parts of Africa that get a lot of rain. But that part of Africa tends to be very dry. And there's very good reason, and it's something that we're going to be learning about in these videos, why that part of Africa gets so much rain. But would you believe if we go back as little as 6,000 years, that what's underneath that sand would be rocks that show us that that area was once a very diverse rainforest. So the Sahara Desert at one point was actually a rainforest. And what's even more amazing about that is that if we go back even further in time and to millions of years ago, possibly even billions of years ago, that part of Africa would have actually been under ice. So as things change on the earth, climates change as well. Climate change usually is very, very slow. And when it's very, very slow, it's actually a good thing that it's slow because it gives life the ability to adapt and change with it. What you don't want to happen is to have a climate in an area change suddenly. If it changes suddenly, life can't keep up. It can't evolve with the change in the weather, and that's where we get extinctions of different life forms in certain areas. So that's something that climate is very important for us to be watching closely. It's something that scientists are keeping a very big eye on because it's one of the top concerns of all the world leaders today is that the climate doesn't change so much so suddenly that we're not able to adapt to it. Because if we can't adapt to it, we can't grow crops. If we can't grow crops, we can't raise cattle. If we can't raise cattle, we're not going to have food. No crops, no cattle, no food. So this is something climate we need to keep a close eye All right, let's dig a little deeper into the atmosphere. How does it work? How does it behave? What's it made up of? Let's start with what it's made up of. What's its composition? Do you know what the number one gas in our atmosphere is? And I feel like I've asked this question in my class a couple of times already, but it still surprises a lot of people. Is it oxygen? No. No, oxygen, believe it or not, is not the number one gas in the atmosphere. That's typically when I ask my students, that's the number one gas. They mostly think that it's oxygen. And I think most people believe that oxygen is the number one thing because we need it so much. Well, it must be carbon dioxide because, carbon dioxide is greenhouse gas. And that greenhouse gas, you've heard about the greenhouse gases before, so there must be carbon dioxide in the atmosphere. Nope, not even close. And it's not water either. That might be kind of a third outlying gas, I guess, that you're looking up in the sky and there's clouds and stuff like that. Could it be water? I mean, we know there's water vapor in the air. Nope, it's not water. So what is it? Well, strangely enough, the number one gas in the atmosphere is nitrogen. It's two nitrogen atoms bound together. And it makes up 78% of the air that you are currently breathing. So most of the air that you're breathing right now is nitrogen. And you think, well, geez, Mr. Lee, I mean, why aren't we suffocating? Is nitrogen bad for us? Should I not be trying to breathe out at night? Well, the thing about nitrogen is it doesn't affect anything. It doesn't cause things to rust. It doesn't cause things to decay. It really is what's called an inert gas. And an inert gas is a gas that basically is not reactive. So you can breathe it in and breathe it out. You'll breathe it in through your nose, gets into your lungs, it just sits in your lungs. It doesn't react in anything in your body, and then you just breathe it out. So it's no big deal. Now, plants and stuff like that, as nitrogen seeps into the ground, the roots know how to fix the nitrogen to break those bonds and use it for growth. So it's important for plant growth. But as far as it in the atmosphere, it's really what's called an inert gas, a non-reactive gas. So it really doesn't affect us that much. The number two, and you can see the number two gas, and by quite a bit, is 20% of that is oxygen. Oxygen takes up really 21%, at 20.9, when you round it off, 21% of the atmosphere that we have right now is oxygen, and that's what makes Earth unique, is that we do have so much more oxygen. Now, we don't want to have too little oxygen because we need oxygen to breathe. So that's why we need trees and stuff like that. But also, you can't have too much oxygen, because if you have too much oxygen, one of the top things that would happen if you have too much oxygen is if you have, say, a forest fire. Well, fire requires oxygen in order to burn. If you put too much oxygen into the atmosphere, yeah, it's better for us to breathe, but it also is better for fires to breathe. So where you have maybe a small forest fire, if we increase that oxygen up to maybe 22, 23, 24, 25%, a small forest fire could turn into an epic disaster very, very quickly. And then you look and see the rest of what's there. And I just realized that my picture is probably over a whole bunch of these things that you're supposed to be reading. The rest of what you can see there is that really almost 1%. If you take 78 and 20.9, really 21%, this is 1% of everything else. And look at that, carbon dioxide. Carbon dioxide is 0.03% of all the gases in the atmosphere. And it's so important because carbon dioxide is what's called a greenhouse gas. I'm going to talk more about those, definitely talk more about those later. But a greenhouse gas takes in sunlight and converts that sunlight into heat. Nitrogen doesn't do that. Oxygen, depending on the form of oxygen, it doesn't do it. But carbon dioxide, is, for the most part, will take in sunlight, the radiation from the sun, and turn it into heat. And that's what keeps us warm. So carbon dioxide at that percentage is very important, and it's a very natural gas. Aside from human beings putting it out, it comes out of volcanoes, it comes out of decaying matter. There's a whole bunch of different ways carbon dioxide gets into the atmosphere, but that's natural. However, the thing that we do concern ourselves about is, because it is taking in sunlight and turning it into heat, if we increase that 0.03% of carbon dioxide, that's going to significantly change and alter the temperature of the air. Well, if you significantly change and alter the temperature of the air just 1 or 2 degrees, that causes climates to change. And if it happens too fast, we can't adapt to it, and that's a big problem. So that's something that we'll be definitely talking about in the future. Carbon dioxide is important. It does keep us warm, but we can't have too much of it. Then you have the other gases, the water vapor, argon. Argon is a type of really radioactive gas. Yep, you're breathing a radioactive gas. Don't worry, it's not going to kill you. That's put off by granite rocks. Like I said, it's not going to kill you unless, of course, you live in a place that actually is built on granite rocks. So if you live in a place like, say, Missoula, Montana has a very big granite outcrop there, and you've built your house on top of a granite outcrop, puts out a lot of argon gas, they actually have argon detectors in houses to determine whether or not there's too much argon gas, and it's almost kind of like carbon monoxide things that we have here. It's you need to leave if you got too much argon gas that's going on. All right, and I think we're just about towards the end of today, but this is actually really an important slide. I don't have a lot of writing on it. But what it does is it shows you the different layers, the characteristics of our atmosphere. And, oops, go back, not yet. Let me move my picture over here a little bit. Turns out that our atmosphere is layered, and each one of these layers of air really have different characteristics, different compositions. If we start down here at the troposphere, and you can see that this is the troposphere goes from the surface, sea level, all the way up to about 9-10 miles ish. It varies. In fact, it actually moves up and down depending on where you're at. The troposphere is important to us because that's where we live. It is also where really all the weather takes place. You'll notice that all these other layers, you don't really see much for clouds. These other different types of clouds, these noctilucent clouds, are not water vapor clouds. They're more kind of closely related to like the aurora borealis or northern lights. Polar stratospheric clouds, that's something that's really only happens at the pole because the atmosphere is really thin up there. But if you look down here, this is where we get even the highest of high clouds. The highest clouds that you see with your eyes will be these what's called cirrus clouds. Stratocumulus clouds, these are clouds that we're kind of familiar here in the Pacific Northwest. If you go back into the middle of the United States, you get them every once in a while here, but you'll get these big old cumulonimbus clouds. Even has this anvil head, and there's a reason for that anvil head. Those cumulonimbus clouds are where the big rainstorms, hailstorms, possibly even tornadoes happen. But this is where all the weather is, and this is really about as high. What happens is that airplanes like to fly at the top of the troposphere. The reason why they like to travel at the top of the troposphere is a couple of different things. Number one, this is where all the weather's taking place. This is where we get all the, is it windy or is it calm? Do we have clouds? You want to fly above the clouds because there's a lot of air movement inside of a cloud. The other thing that's happening is by the time we get up to this next layer called the stratosphere, that is where the air is allowed to move. It doesn't have to go over trees and mountains and buildings. And that friction from trees and mountains and buildings actually slows the air down. So when you get above the troposphere and start getting into the stratosphere, the airspeed picks up. And so the air is blowing, in this case, from right to left. It's going to be beneficial for that commercial jet to go up into that air and let the tailwind blow at this direction. And if you look at things like these cumulus clouds, here it's lifting up moisture and pushing the moisture up. It gets up to the stratosphere, and that stratosphere, the wind is blowing so hard, it's actually going to blow the top of the cloud off. So it actually takes away from the top of the clouds. It's called an anvil cloud. So if you ever see an anvil cloud, these big old cumulonimbus clouds with this flat top to it, you know that that cloud is so tall that it's reached the next layer. Now the next layer contains something. Inside the stratosphere, we have this small layer called the ozone layer. Now the ozone layer is oxygen, but it's not the oxygen that we breathe. The oxygen that we breathe is O2, which is two oxygens held together. In the ozone, we have a situation where we have three oxygens that have been bound together. And what's important about the ozone layer is that, like carbon dioxide, it's a greenhouse gas. Bad down here in the troposphere, but up in the stratosphere it's really important, because in the stratosphere, what's going to happen with that ozone layer is it's going to take in dangerous radiation from the sun. Radiation from the sun that we don't need. Radiation from the sun, ultraviolet radiation is the type of radiation I'm talking about, that if you're like me, you're very concerned about, because it's the type of thing that causes things like skin cancer. And even more important than that, it goes beyond just skin cancer. If you get too much radiation, it actually starts affecting the DNA of things, even like animals and other plants. So we have to protect ourselves from the ozone, not the ozone layer, but we have to protect ourselves from that dangerous ultraviolet radiation coming through. The cool thing about ozone is that ozone will actually absorb that radiation and turns it into heat. Now, how do we know it's turning it into heat? Well, if you let go of a balloon and that balloon started going up and up and up and up, if you could imagine, the temperature of that balloon is going to go down, down, down. The further you get away from the surface of the Earth, the cooler it gets. And that's what this line is that you're looking at right here. Right here, this line right here is showing what the average temperature. So on the Earth's surface, a nice day would be about 20 degrees Celsius. And as you start going up, like if you were flying up in an airplane, the further you got away from the surface of the Earth, the colder it gets. So typically when you're flying in a plane, even if it's summer, you're probably flying in temperatures that are well below freezing until you get up to the stratosphere. When you get to the stratosphere, we have what's called the tropopause right here. And that's where, this is called the environmental lapse rate. This is the steady rate in which the air temperature decreases with altitude, the higher you go. But then you notice that the temperature stables off. It doesn't get any colder. It stays about the same temperature as we go higher and higher through the stratosphere. Then we hit that ozone layer, and look what happens here. This is actually pretty amazing. That ultraviolet radiation is being absorbed by ozone, and that ozone, remember, it doesn't just suck it in and keep it in. It converts that energy from one form into the next. It converts it from radiation energy to thermal energy. And because it's converting it to thermal energy, that temperature is going to be increasing. And it starts to increase, never gets as warm as the surface of the Earth, but all the way going up to the stratosphere, that temperature starts to increase. And that's because of the amount of ozone inside of the stratosphere. Then we start getting into the mesosphere. Now the air up here is really thin. It would be impossible for us to breathe, really impossible for us to breathe even down here at this point. So the air up here is really thin, not as much ozone anymore. And because of that, it starts to go down. So you can see the temperature once again gets cooler and cooler and cooler, well into the well below freezing temperatures, into the negative 60s, the 90s. Then we get up into the thermosphere. Now this is a little bit misleading. Above the thermosphere, now the mesosphere, meso means middle. That's where you see things like meteors. When you see that flash of light at night, it's just a small rock. It's hitting the atmosphere. It's going so fast that the friction from the atmosphere burns it up. And it burns up before it even really hits the stratosphere. If it hits the stratosphere, it must have been a pretty sizable rock. We're talking maybe something about this big versus that big. But when we get up into the thermosphere is really defines the outermost part of our atmosphere. And at this point, the air is so spread out and so sparse, you can see the temperature starts to increase a little bit. But that's a little bit misleading, because it would actually feel colder in the thermosphere than it would be in the mesosphere. In the mesosphere, there's still enough air where the air particles are touching together. And the thermosphere, the air particles are now so spread out, so thin, that they're likely not to touch each other. So why does the temperature seem to be higher up there? Why does it seem to be going to a greater temperature? Well, we have to measure at this point. We can't just go up there with a thermometer because a thermometer won't work. We have to measure the temperature of the actual molecules themselves. And because the molecules themselves are getting hit by solar radiation right away, they're the first ones to get warmed up by that solar radiation. So it's a little bit misleading to think that the thermosphere is warmer. The particles are warmer, but the temperature is so spread out that you wouldn't feel the warmth. That's kind of like saying that the average warmth of everybody in a cold classroom, that everybody's warmth is, normal temperature, 98 degrees. Well, if you're cold in that classroom, but the average temperature of all the people in the classroom is 98 degrees, the only way that you're going to be warm in that classroom is if everybody's huddled together and you're all touching each other. But if you're all spread apart, you're not going to feel that warmth. And that's what it's like for the particles inside the thermosphere. They're all so spread apart that you won't feel them. Okay, and I think this is the last slide. So that's where we're going to end today. So we've talked about what the difference between weather and climate is. We've talked about the temperature of the atmosphere. We've talked about the different layers of the atmosphere and how they differ from each other. We've also talked about the composition for the atmosphere. So that gives us a good understanding of what's going on with the atmosphere. For the next video, what I plan on doing is learning more about the relationship. And I like this picture right here because this picture shows the relationship between the sun and the earth. And that's important because all weather is driven by the sun. All weather, let me say that again, all weather is driven by the sun. If there was no sun, we would have no rain. If there was no sun, we would have no wind. If we had no sun, the temperature would just be cold and all the air would settle, and the air would settle into perfect layers and it wouldn't get moved around. We would freeze like we would freeze on Mercury at night and fry during the day. Well, actually, we wouldn't fry during the day, I guess, because we wouldn't have any sun. So the interaction between the sun and the earth is really important, and it explains why we have seasons, but not just why we have seasons. Why is it hotter at the equator versus the North Pole? Why is it during the summer it gets warm and dry, but during the winter we're kind of cold and wet? That's the thing that we're going to be talking about, I hope tomorrow or Friday, by the time I get the next one done. So I hope you guys have enjoyed this. When I put this on YouTube this time, I did it last time. I guess I didn't have the place to have comments. This time it'll have comments, and I hope you guys will leave some comments in there. Don't criticize the banjo in the background or the banjo singing. But maybe if you have questions that you want to know, I'd be happy to answer those. And don't forget Remind.com. You guys can text me anytime you want. I hope you guys are having a great break. And I do miss you guys. Love you guys. You guys take care.